Welcome back to the deep dive. Today, we are really digging into the future of making fresh water, specifically looking beyond conventional desalination CMD, which is, let's face it, pretty energy intensive.
It really
We're
is.
moving into something more sustainable, solar-powered membrane distillation, or SPMD. And this isn't just a small improvement we're talking about.
No, absolutely not. It's more of a fundamental shift in how we approached the thermal process itself.
So let's set the stage. Why is this so critical? The global water situation, it's stark.
It really is. The numbers are quite sobering. Our sources point to around 2.2 billion people lacking safe drinking water access right now.
2.2 billion.
And it gets worse for sanitation.
Oh.
4.2 billion people don't have proper sanitation facilities. That puts incredible pressure on resources.
And the market's reacting, right? Desalination demand is projected to shoot up.
Oh, massively. We're seeing projections of something like a 74% increase worldwide, particularly in places like the Mediterranean region, Middle East, North Africa, and parts of Europe.
Mm-hmm.
But you can't just meet that demand with the old energy-guzzling methods. It has to be sustainable.
That's the core issue with conventional processes, isn't it? Heavy reliance on centralized power, often fossil fuels, lots of emissions, complex operation.
Exactly. And that's where SPMD offers such a compelling alternative. It integrates solar energy directly.
Which brings down costs, obviously, but also enables access in places that are off-grid, remote,
Right.
places where a big centralized plant just isn't feasible.
Precisely. It democratizes access to fresh water, potentially.
Okay, so before we dive into SPMD, let's quickly ground ourselves in the basic technology membrane distillation, MD. How does that work at its core?
Sure. So MD is thermally driven. You have your feed water, which is heated on one side of a special membrane. This membrane is hydrophobic. It repels liquid water.
Okay.
Because of a temperature difference across that membrane, water evaporates from the hot feed side. The resulting water vapor then travels through the membrane's tiny pores.
Got it. Vapor, not liquid.
Correct. And then it reaches the colder side, the permeate side, where it condenses back into pure, liquid, fresh water. The temperature difference is the driving force.
What makes MD stand out compared to, say, the workhorse technology, reverse osmosis, especially in tricky situations?
Yeah, MD's big advantage is its robustness. It can handle extremely high salinity feeds, think brines, industrial wastewater, much better than RO.
Why is that?
Because the driving force, the vapor pressure difference, isn't really affected much by the salt concentration in the feed. RO struggles with high osmotic pressures from salts. MD also tends to be more resistant to certain types of fouling.
So it's great for niche, tough applications, food processing, pharma, environmental cleanup.
Exactly. Often used where RO might fail or require extensive pretreatment.
But coming back to conventional MD, CMD,
Yeah.
it's always had this energy Achilles heel.
Mm.
You mentioned centralized heating, fossil fuel.
That's the crux of it. You're heating a large volume of water in a central unit, then pumping it to the membrane modules.
And you lose heat along the way.
Inevitably, you get conductive and convective heat losses during that transfer. Plus, the whole process of heating that bulk water is just inherently energy intensive. Think about the heat capacity of water.
Right. You're pouring energy into the whole volume, not just the bit that needs to evaporate.
Exactly. And this is where SPMD represents such a breakthrough. The sources are clear. By integrating solar energy and using photothermal materials right on the membrane.
You heat it locally.
Yeah.
Right where the action happens.
Precisely. You're delivering the thermal energy directly to a photothermal layer on the membrane surface. This completely bypasses those bulk heating losses.
And the efficiency numbers reflect that.
Dramatically. We're talking about achieving thermal energy efficiencies in the range of 60 ppm, 10%, 60% plus or minus 10.
Okay, compare that to CMD.
Conventional MD systems often struggle to get above 10% thermal efficiency, sometimes well below that.
So a 5- or 6-fold improvement, that's not incremental.
No, it's transformative, like you said. It changes the game.
Okay, so our mission for this deep dive is clear. We need to get into the weeds on the principles, the different ways SPMD systems are configured, the critical material science behind these new membranes, and importantly, the techno-economics. Does SPMD really have what it takes to overtake CMD?
That's the core question we need to explore.
All right, let's start with the fundamental problem that SPMD solves so elegantly. Temperature polarization, TP. Why is this such a killer for conventional MD?
Right, TP. You really can't understand the benefit of SPMD without grasping why TP is so detrimental in CMD. It's an inherent phenomenon, basically unavoidable in the conventional setup.
What's the mechanism? You mentioned heat and mass transfer.
It comes down to two things happening right at the membrane boundaries. First, you have conductive heat transfer through the membrane material itself and the adjacent water layers. Second, and crucially, there's the latent heat of vaporization.
Ah, the energy needed for water to turn into vapor.
Exactly. As water evaporates on the hot feed side of the membrane, it consumes a significant amount of energy, the latent heat. This localized energy draw cools down that specific boundary layer of water right next to the membrane surface.
So even if your bulk feed water coming in is hot, the water right at the surface where evaporation happens is cooler.
Significantly cooler. We call the bulk feed temperature $T, but the temperature right at the feed membrane interface, $T, is lower, T-POA.
Okay. And something similar happens on the other side.
Yes, the reverse. When the water vapor condenses on the permeate side, it releases that latent heat. This warms up the boundary layer on the distillate side.
So the membrane surface on the distillate side is warmer than the bulk distillate.
Correct. The distillate membrane interface temperature is higher than the bulk distillate temperature, T.
And the driving force for the whole process is the temperature difference across the membrane.
Which means the actual effective temperature difference driving evaporation and vapor transport isn't the easily measured bulk difference, T/TDD. It's the difference right at the interfaces.
TDD.
And because TDF is lower than TD and TD is higher than TD, that interface difference is much smaller.
Drastically smaller. That's temperature polarization. It essentially undermines the theoretical driving force you thought you had based on the bulk temperatures.
And this gets worse as you try to scale things up.
Yes, because managing those boundary layers effectively over larger areas becomes very difficult. This reduction in driving force is often quantified by the temperature polarization coefficient, or TPC, which basically tells you how much of your potential driving force you're losing.
Historically, how did engineers try to fight TP in CMD?
The main approach was to increase turbulence in the feed channel. Things like modified channel designs or putting in feed spacers, basically objects to disrupt the flow and mix the water near the surface.
But that sounds like it would increase the pressure drop, meaning you need more powerful pumps. Exactly the problem. You might slightly reduce the thickness of that cool boundary layer, improving the TPC a bit, but you'd spend way more energy on pumping.
So you're robbing Peter to pay Paul, energy-wise.
Pretty much. It counteracted the whole goal of making MD a low-energy process. It was a band-aid, not a solution.
Okay, so this is where photothermal membrane distillation, PMD, comes in as the elegant answer. How does it tackle TP head-on?
PMD uses these photothermal materials, nanoparticles, special coatings, integrated directly onto or into the membrane. Think of them as tiny, nanoscale heaters embedded right where you need them.
And they're powered by sunlight.
Correct. They absorb incoming solar radiation very efficiently and convert that light energy directly into heat. Critically, this heating happens at the membrane surface.
So instead of heating the bulk fluid far away, you generate heat at the interface.
Precisely. And this completely flips the script on temperature polarization.
So.
Because the heat is generated right at the feed membrane interface, that interface temperature, T of MD, now becomes higher than the bulk feed temperature, T vollars.
Ah, so you're reversing the problematic temperature gradient, DTMTF, caused by evaporative cooling in CMD. Now you have TCAMT.
Exactly. You're generating the heat precisely where evaporation occurs, overcoming the latent heat loss locally and establishing a highly efficient temperature gradient across the membrane pores. You're no longer relying on heat conducted from the bulk.
That sounds incredibly efficient. You avoid heating the entire bulk feed, minimize heat loss during transfer.
And you directly combat TP. This allows PMD systems to operate much more effectively, achieving higher flux and better thermal efficiency.
Plus, I read something about lower operating temperatures being beneficial.
Yes, that's another significant advantage. Because the bulk feed water doesn't need to be heated as intensely, the overall operating temperature of the system can often be lower than in CMD for the same flux.
And lower temperatures mean less trouble with scaling and fouling on the membrane surface, things like calcium carbonate precipitating out.
Exactly. It leads to potentially longer membrane life and less downtime for cleaning. So PMD tackles the energy efficiency, the TP problem, and potentially improves operational stability.
Okay, that makes the fundamental advantage crystal clear. Let's talk about how these systems are actually built. How is solar energy integrated? Our sources mention two main categories, direct and indirect.
Right. You can think of it as either using solar energy in a separate external step, indirect, or integrating the solar collection right into the desalination unit itself, direct.
Let's start with the indirect approach. What does that typically involve?
This usually means using dedicated solar collectors to capture solar energy, typically as heat. Common examples are flat plate collectors, good for moderate temperatures, maybe up to 60–70 degrees C.
Okay, standard solar water heater tech.
Pretty much. For higher temperatures needed for better MD performance, you might use evacuated tube collectors. The vacuum insulation reduces heat loss, letting them reach maybe 90 degrees C or so.
And for really high temperatures?
Then you're looking at concentrating collectors, like parabolic troughs. These focus sunlight onto a receival tube and can get well over 120 degrees C, but they're more complex, need solar tracking systems.
Right, more moving parts, higher cost. What about solar ponds? That sounds intriguing. Using salt layers to trap heat.
Yeah, solar ponds are a fascinating large-scale concept. You basically create 3 layers of water with different salt concentrations in a large basin.
How does that trap heat?
The bottom layer is very salty and dense. The top layer is fresh or low salinity. In between, you have a gradient layer where salinity increases sharply with depth.
And the salt gradient stops convection.
Exactly. The density gradient suppresses natural convection, which would normally bring heat from the bottom to the surface where it would be lost. So sunlight penetrates the top layers, gets absorbed by the dark bottom layer, and the heat gets trapped down there.
How hot can it get?
Temperatures approaching boiling, near 100 degrees C, are possible in the bottom layer. This stored thermal energy can then be extracted to drive a desalination process, like MD, or even generate electricity using special turbines.
Is maintaining those salt layers difficult?
It requires careful management, yeah. You need to prevent mixing from wind or temperature fluctuations and manage salt diffusion. But it's a way to get large-scale thermal storage.
And there's a synergy with desalination brine, right?
Yes, the concentrated brine rejected from desalination plants is a potential source for the high salinity bottom layer of a solar pond. It reduces the need to add as much salt.
So these indirect methods often lead to hybrid systems, combining solar thermal with MD or using solar PV.
Correct. You might have solar thermal collectors providing a steady supply of hot feed water to the MD unit. Or you could use photovoltaic PV panels to generate electricity off-grid.
Powering the pumps and controls.
Exactly. Usually integrated with batteries for energy storage and inverters to manage the power. So indirect means solely energy is captured externally first.
Okay, now let's move to the direct approach. Heating and desalination happening in the same unit. How does that work?
Here, the key distinction is where the solar absorption happens within the unit. The more traditional direct method involves heating via an absorbing surface.
So like a mini flat plate collector built into the MD module.
Kind of. You typically have a dark solar absorbing plate positioned beneath a transparent cover, like glazed glass. The feed water flows in a channel between this hot absorber plate and the membrane.
Simple concept, but what's the catch?
The big limitation is that to effectively heat the water this way, especially with direct sunlight, you need the water to flow quite slowly. You need sufficient residence time for it to absorb heat from the plate.
But slow flow rates are bad for temperature polarization in conventional setups.
Precisely. So this traditional direct approach, while simple, often suffers badly from TP because of the required low flow rate. The slow-moving water develops that thick, cool boundary layer right next to the membrane, killing the driving force.
Seems counterintuitive.
It is a significant drawback. However, this structure is used cleverly in some integrated PV-MD devices.
Okay, unpack that. Using waste heat from solar panels.
Exactly. Solar PV cells get hot during operation, which actually reduces their electrical efficiency. So the idea is to integrate MD channels directly behind the PV cells.
So the feed water for the MD cools the back of the PV panel.
Right. The waste heat from the PV cell heats the feed water in the first stage of a multi-stage MD system integrated behind it. It's a win-win. You cool the PV cell, boosting its electrical output. Studies show maybe a 4.5% increase.
And you get free preheating for your MD process.
Correct. A 3-stage PV-MD device using this waste heat reportedly achieved a respectable permeate flux of about $1.79 tech-sun under standard sunlight conditions.
Clever integration. But the real game changer, the core innovation we discussed, is the other subcategory of direct heating.
Yes, membrane surface heating. This is where PMD and related concepts like nanophotonic-enabled solar MD, NESMD really shine.
Remind us why this is fundamentally different.
Because here, the photothermal material isn't on a separate plate, it's coated directly onto the membrane surface itself. or sometimes integrated within the top layer of the membrane structure.
So the sunlight is absorbed and converted to heat exactly at the water membrane interface where evaporation needs to happen.
Precisely. You minimize heat loss to the surroundings, you dramatically reduce the thermal resistance involved in heating bulk water, and you directly counteract TP by generating heat locally.
Leading to better flux and efficiency.
Significantly better. It's a much more effective way to utilize solar energy for MD.
Besides solar absorption, are other localized heating methods being looked at?
Yes, researchers are exploring things like joule heating, passing an electrical current through a conductive layer on the membrane, or induction heating, using magnetic fields to heat embedded nanoparticles. But solar photothermal is the main focus for SPMD due to the free energy source.
What kind of materials are enabling this surface heating?
It's a rapidly evolving field. We're seeing things like silver nanoparticles, AGNPs, versatile coatings like polydopamine, PDA, good old carbon black, CB, magnetic iron oxide, Fe304-1, and highly efficient materials like titanium nitride, 10I. The goal is broadband absorption and efficient light-to-heat conversion.
Okay, this brings us squarely to the membrane itself. For a technical audience, the specific characteristics required for SPMD membranes are crucial. This isn't just any filter paper.
Absolutely not. The demands are quite rigorous, especially balancing heat transfer, mass transfer, and long-term stability under direct solar exposure. There are about 6 key characteristics we need to consider.
Let's start with the surface properties. Hydrophobicity is obviously key for MD. How's that measured and what's needed?
Right. The membrane must be non-wetting. This is typically quantified by the water contact angle, theta dollars. You need theta dollars to be greater than $90.
Right.
The higher, generally, the better.
Are new materials pushing beyond standard PTFE?
Yes. Things like electrospun styrene, butadiene styrene, SPS polymers, are showing even higher hydrophobicity than some commercial membranes. But hydrophobicity alone isn't enough. You need to consider the liquid entry pressure, or LEP.
LEP. That sounds like the pressure needed to force liquid water into the pores, which you definitely don't want.
Exactly. It's a critical measure of the membrane's resistance to wetting under operational pressure. For reliable MD operation, you generally need an LEP greater than, say, 2.5 bar.
What determines the LEP?
It's governed by the Laplace equation. Essentially, LEKDY is proportional to the liquid's surface tension and the cosine of the contact angle, and inversely proportional to the maximum pore radius.
Okay, so LEPWBP, where B is a geometric factor. The key thing there is the inverse relationship with pore size. Smaller pores mean higher LEP.
Correct. Smaller pores resist wetting better. But here's the classic MD trade-off.
Right. For good performance, high water vapor flux, you want larger pores and higher porosity, don't you?
You do. Larger pores offer less resistance to vapor flow. This brings us to pore size and porosity. Ideally, pore sizes are in the range of 0.1 to 1 micrometer. 1 and 1 wins.
And porosity, how much void space?
You want high porosity, typically around 80%, although the range can be maybe 40–90%. Porosity is often calculated using the Smolder-Franken equation based on polymer and membrane densities.
Why is high porosity so important, besides just allowing vapor through?
High porosity significantly reduces the conductive heat loss through the membrane structure itself. Remember, those pores are filled with air or water vapor, which are excellent insulators compared to the solid polymer. So high porosity enhances flux and thermal efficiency.
So the design challenge is achieving high porosity with pores that are large enough for good flux, but small enough to maintain a high LEP, a balancing act.
A critical balancing act, often managed by aiming for a narrow pore size distribution within that optimal range.
What about membrane thickness? How does that play a role?
Thickness directly impacts the path length for vapor diffusion. Thicker membranes mean higher resistance to vapor flow, which reduces flux. The typical range is maybe $100 to $700, remember.
Is there an optimal thickness?
It's highly dependent on the application, particularly the feed concentration. Interestingly, one study found for low salinity feeds less than 10.8% ACL. The optimal thickness was surprisingly thin, around $13, remember.
13 microns. That's incredibly thin. Suggests potential for very high flux in brackish water applications.
Potentially, yes. It highlights that you need to tailor the membrane structure to the specific feed condition.
Okay, next. Thermal conductivity. For SPMD with localized heating, you want this to be as low as possible, right? To keep the heat at the surface.
Absolutely crucial. You want the membrane material itself to be a poor conductor of heat. Polymers are naturally pretty good insulators, typically in the DARE 11 Pol 5 tolerable range.
And again, high porosity helps here.
Immensely. The trapped gas in the pores significantly lowers the overall effective thermal conductivity of the membrane structure. This helps maintain that desired reverse temperature profile by preventing the photothermal heat from immediately conducting back into the bulk feed.
Makes sense. Finally, stability. SPMD seems like a harsh environment. Direct sun, potentially hot water, complex feeds.
Stability is paramount. You need excellent thermal stability to withstand the focused solar heating and chemical stability to resist degradation from the feed water components and UV radiation over long periods.
And anti-fouling, anti-scaling properties become even more important.
Yes, because any fouling layer can interfere with light absorption or block pores, so robust anti-fouling and anti-scaling characteristics, perhaps through surface modifications, are essential for long-term reliable SPMD operation.
Okay, we know the properties we need. How do engineers actually make these specialized membranes, especially incorporating the photothermal materials? Two main routes, one-step and multi-step.
Correct. One-step methods basically create the membrane with the photothermal material integrated throughout the structure in a single process. This leads to what are called mixed matrix membranes, or MMMs.
How is that done?
Common techniques are electrospinning, which creates nanofiber mats and seems quite popular for SPMD research, and non-solvent-induced phase separation, NIPS, a more traditional phase inversion method. In both, you disperse the photothermal filler particles into the polymer solution before forming the membrane.
What's the main advantage of doing it all in one go?
The biggest advantage is that the photothermal materials are physically locked within the polymer matrix. This minimizes the risk of them leaching out into the AVE or permeate water over time. You get uniform incorporation.
Sounds good, but what's the downside? I recall reading critiques about material usage.
That's the major drawback. Because the filler is distributed throughout the entire membrane thickness, a large portion of it is buried deep within the structure, far from the surface.
Where it can't actually absorb sunlight or contribute to surface heating.
Exactly. So you end up needing a much higher overall concentration, a larger volume of potentially expensive photothermal material compared to just applying it to the surface. Much of it is effectively wasted from a photothermal perspective.
So a trade-off between potentially higher material cost and guaranteed filler retention.
Precisely. For applications like drinking water, ensuring no nanoparticle leakage might make the MMM route preferable, despite the higher material cost. Plus, it offers flexibility in polymer choice. You can use PVDF, SBS, various copolymers.
Okay, what about the multi-step methods? These focus on modifying just the surface.
Right. The idea here is to deposit a thin, functional photothermal layer onto a pre-formed pore support membrane. This uses the expensive materials much more efficiently.
What techniques fall under this?
Several. One is plasma treatment. This uses ionized gas, like a fluorinated monomer plasma, to chemically modify the membrane surface.
To increase hydrophobicity, for instance.
Yes, or to graft specific functional groups. For example, TechCF for plasma treatment was shown to increase the contact angle of a PS membrane by over 50%, boosting its performance.
Downsides.
Plasma reactors are expensive, high vacuum equipment, so scalability and cost can be issues for large-scale production, although it offers precise surface control without affecting the bulk membrane.
Another approach uses polydopamine, PDA. You mentioned it earlier as a material, but here it's used as a sort of universal glue.
PDA is incredibly versatile. It's inspired by muscle adhesive proteins and can self-polymerize onto almost any surface, forming a thin, adherent coating.
And it's photothermal itself.
Yes, it absorbs light well, but its real strength here is as an intermediate adhesive layer. You can coat a membrane with PDA and then easily attach other functional materials onto the PDA layer, things like carbon black nanoparticles for enhanced heating, or maybe a superhydrophobic molecule like FAS17 to improve wetting resistance.
So it's a platform for building multifunctional surfaces.
Exactly, and it's relatively simple, uses water-based chemistry, and PDA itself is biocompatible. A PDA-based coating achieved over 75% solar energy utilization efficiency in one study. Very promising.
What about simpler methods like dip coating? Just dipping the membrane into a dispersion.
Dip coating is straightforward and potentially scalable. You immerse the membrane in a solution or dispersion containing the photothermal material, and then control the withdrawal speed and drying conditions to form a thin layer.
Was this used for those Janus membranes you mentioned?
Yes, it's one way to create them. Remember, Janus membranes have two different faces. Dip coating can be used to apply a specific functional layer to just one side of the membrane.
Let's quickly revisit Janus membranes. Amphiphilic on one side to resist fouling, but hydrophobic overall. How does that work again?
It's clever surface engineering. The feed-facing side is designed to have some affinity for water and oils, amphiphilic, which makes it slippery to organic foulants. They don't adhere strongly. But the pore structure in the permeate-facing side remains strongly hydrophobic to ensure only vapor passes through and prevent liquid breakthrough.
So it tackles fouling and wetting simultaneously, and dip coating enabled that.
It's one feasible method. The study you cited showed stable operation for 10 hours using such a structure, which is promising for dealing with challenging feed waters.
Okay, last method, vacuum filtration. Sounds simple too.
It is, operationally. You take a dispersion of your photothermal material and filter it through the support membrane. The material gets deposited onto the surface, forming a layer.
And you control the thickness easily?
Yes, by adjusting the concentration of the dispersion or the volume filtered. It's great for lab-scale development and has been used to deposit high-performance materials like MZenes, which showed a rapid temperature rise. Bio-derived materials like PDA bacterial nanocellulose films have also been applied this way.
What's the catch with vacuum filtration?
The main challenge is scalability. It's typically a batch process, and the size of the membrane you can produce is limited by the filtration setup. Making large, continuous sheets might be difficult.
So a range of fabrication options, each with its own cost, scalability, and efficiency trade-offs. Seems like surface modification generally offers better material efficiency if you can get the adhesion and durability right.
That's a fair assessment. The goal is always a durable, highly efficient photothermal layer using the minimal amount of material.
All right, let's dive deeper into the actual photothermal materials themselves. You mentioned the 70% energy cost burden of conventional heating. These nanomaterials are the key to slashing that. Which ones are leading the pack?
Unquestionably, carbon-based materials have received the most attention. We're talking graphene, graphene oxide, GO, carbon nanotubes, CNTs, reduced graphene oxide, RGO, and just simple carbon black, CB.
Why carbon? What makes it so good for this?
Its electronic structure. Carbon materials, especially graphitic ones, have loosely bound electrons, pi electrons, that can absorb light across a very broad spectrum from UV through visible and well into the near infrared, which contains a lot of solar energy.
Broadband absorption. Plus, they're generally stable and relatively low cost, right? Especially carbon black.
Generally, yes. They convert that absorbed light into heat very effectively. Adding them to membranes like CNTs has shown flux enhancements of 12–40%. Simple spray coating of carbon black NPs onto PVDF reportedly raised the surface temp by almost 14 degrees C in under 3 minutes under standard sunlight.
Sounds ideal. But you mentioned concerns earlier: cost, stability, health hazards. Let's unpack those. If carbon black is cheap, what's the cost issue?
The cost issue relates more to the highly purified or structured forms, like high-quality graphene or well-aligned CNTs. Producing those consistently at scale is still expensive.
And alignment is important for CNTs.
It can be for maximizing certain properties. Then there's the long-term stability. How well do these materials hold up under constant UV exposure and thermal cycling? And crucially, the potential health risks if nanoparticles were to detach and get into the water supply.
The regulatory pathway for nanomaterials in drinking water is still pretty murky.
Very much so. So while carbon materials offer excellent performance now, there are significant questions about their long-term commercial viability and safety that need to be addressed.
Okay, moving on. What about metal oxides? Things like titanium dioxide, zinc oxide, zeno, iron oxide. Metal oxides are attractive because they are generally considered stable, abundant, and low toxicity. They work as semiconductors.
How do they generate heat?
They absorb photons with energy greater than their band gap, creating electron-hole pairs. When these pairs recombine or relax, they release the excess energy as heat. They can also induce surface nanoroughness, which can help with anti-wetting properties.
But what's their limitation compared to carbon? Their main limitation is that they are typically narrow bandgap semiconductors. They only absorb light effectively within a specific wavelength range, usually UV or parts of the visible spectrum.
So they miss out on a large chunk of the solar spectrum, particularly the infrared.
Exactly. Their overall light-to-heat conversion efficiency integrated across the whole solar spectrum tends to be lower than broadband absorbers like carbon or certain metals. You trade off some efficiency for stability and perceived safety.
Example.
Fexio-44 nanoparticles, for instance, raised membrane temperature by 25 Circ-Texte in 10 minutes. Good, but perhaps not as dramatic as some carbon materials. Functionalized FTO22 was noted more for its anti-wetting properties.
All right, finally, metals and metal organic frameworks, MOFs. Let's start with MOFs. They're known for being porous.
Extremely porous, yes. MOS based on iron, zirconium, aluminum, etc. have incredibly high surface areas. Their value in membranes isn't primarily photothermal, though some might have some light absorption.
So what do they do?
They're mainly used for structural enhancement and surface modification. Adding them can increase wetting resistance coating PVDF with 5 WA% EBTC MOF push the contact angle to 138 turn counters. They can also improve anti-fouling properties due to their specific surface chemistry and porosity, which can influence mass transfer near the surface. And they achieved near-perfect salt rejection.
So MOFs are more about improving the membrane separation performance and stability rather than generating heat.
Generally, yes. Metals, on the other hand, are all about the heat.
How do they work? Plasma and resonance.
Exactly. Nanoparticles of certain metals, especially noble metals like gold and silver, but also others like aluminum, exhibit surface plasma and resonance. When light hits them, it excites collective oscillations of their surface electrons.
Then that generates heat.
This resonant absorption is very efficient at converting light energy into localized heat, essentially joule heating on a nanoscale. Researchers created flexible, thin films of black gold, nanostructured gold, that absorbed 91% of light in the 400-500 millimeter range. Self-assembled aluminum nanoparticles showed over 96% absorption across the entire solar spectrum.
That sounds incredibly efficient. What's the catch?
Cost and stability. Noble metals like gold are obviously very expensive. More common metals like aluminum are prone to oxidation, which can degrade their plasmonic properties over time, especially in harsh aqueous environments. Finding cheap, stable, and highly plasmonic materials is an ongoing challenge.
So a wide palette of materials, each with pros and cons regarding efficiency, stability, cost, and safety. Material selection is clearly a critical design choice.
Absolutely. It dictates the potential performance ceiling of the SPMD system.
Okay, we have the materials, we have the membrane structure. How do the overall system design choices and operational parameters impact performance, especially comparing PMD back to CMD? Let's talk module design first.
Right. The physical design of the module itself matters a lot, particularly in PMD where you're relying on surface absorption. One key factor is the depth of the water layer in the feed channel.
Why does that matter?
Because if the water layer flowing over the photothermal membrane surface is too thick, the water itself can refract and scatter the incoming sunlight before it reaches the active layer.
Reducing the energy that actually gets absorbed and converted to heat.
Exactly. So shallow feed channels are generally preferred in PMD designs to maximize light penetration to the photothermal surface.
What about the photothermal layer itself? Thickness.
It's another balancing act. A thicker layer might absorb more light overall, but if it gets too thick, it can start blocking the membrane pores underneath or increase the thermal resistance within the layer itself.
Impeding vapor flux.
Right. So the ideal is usually a very thin but highly absorbing layer that maximizes light capture without hindering mass transport. The concentration of the photothermal material within that layer is also critical.
You also mentioned earlier that unlike CMD, increasing module dimensions like the length of the channel might actually be good for PMD.
Yes, that's an interesting potential advantage. In PMD, the feed water is continuously heated as it flows along the photothermally active surface. The temperature tends to rise along the channel length.
So the driving force, delta 2, might actually increase further down the module.
It's possible, or at least be maintained more effectively than in CMD, where heat losses dominate over longer distances. This means that scaling up the module length in PMD could lead to a more proportional increase in total permeate production, whereas CMD performance often degrades with increased size.
Okay, that's a significant point for scalability.
Ah.
Now let's hit the most crucial operational difference, feed velocity.
This is fundamental. As we discussed, CMD performance improves at higher feed velocities because the turbulence helps reduce the thickness of the cool boundary layer caused by TP.
You need to physically scrub away that cool layer.
Essentially, yes, but PMD operates on a completely different principle. Because the heat is generated at the surface, PMD actually exhibits greater thermal efficiency at lower feed velocities.
Lower velocities, why?
Because a lower velocity gives the water more residence time in contact with the heated photothermal surface. This allows sufficient time for the localized solar heat to be absorbed and to establish that strong reverse temperature gradient needed for efficient evaporation.
So slow flow allows the surface to get properly hot relative to the bulk.
Precisely. If the water flows too fast, it might not get heated sufficiently at the interface before it moves on.
The engineering implications here seem huge. Lower feed velocity means smaller pumps, less energy spent on pumping.
Exactly. This is a major potential advantage for SPMD. You don't need high-power pumps just to fight TP. You can potentially design simpler, lower-energy systems because the physics of localized heating works better at lower flows. It drastically reduces the parasitic energy consumption associated with fluid handling compared to CMD.
That really underscores the paradigm shift.
Yeah.
Okay, let's explicitly compare CMD versus SPMD scaling, bringing in that nanophotonics-enabled solar MD and ESMD concept again.
Right. This is where the difference becomes stark. With conventional MD, as you try to make the membrane modules larger, longer, or wider to increase production capacity, performance typically drops off.
Why?
Heat losses again.
Primarily, yes. Maintaining uniform temperature and managing TP effectively across a large area becomes increasingly difficult. Heat losses to the environment escalate. The inherent limitations cap practical scalability.
But with any SMD, because the heating is localized right on the nanophotonic surface,
The performance seems to be much less sensitive to module size. The studies you referenced, testing NESMD modules up to 2 meters long, showed that performance remained high.
so doubling the length roughly doubles the output without the efficiency penalty seen in CMD. That's the key finding. Because the effective localized temperature gradient, TFMTS, is maintained along the length, the distillate flow appears to scale much more favorably with module area. NESMD showed greater efficiency than conventional MD for modules up to that 2-meter length tested.
This suggests NESMB could be genuinely viable for larger community-scale desalination systems, overcoming the scaling barrier that plagued traditional MD.
That's the potential, yes. It opens up possibilities that were previously challenging for MD.
And briefly, what about the environmental impact? There was a life cycle assessment, LCA mentioned.
Yes, an LCA study conducted in Jordan compared SPMD, using amorphous silicon solar panels, with conventional MD. The results were pretty definitive.
How so?
The study found that SPMD significantly reduced the environmental footprint across key categories: impact on human health, ecosystems, resource depletion. Compared to CMD, which was set as the baseline with 100% impact, SPMD lowered these impacts by about 80%.
80% reduction, that's substantial.
It really reinforces the sustainability argument for transitioning towards solar-integrated desalination technologies like SPMD. It's not just about energy, it's about the overall environmental burden.
Okay, the technical and environmental case seems strong, but ultimately adoption comes down to techno-economics. How does SPMD stack up financially? Let's start with energy consumption metrics.
This is where we need to be realistic, especially comparing to the dominant technology, reverse osmosis, RO. MD, including CMD and SPMD when considering total energy input, thermal and electrical, typically requires somewhere in the range of $1040 and $33.
How does that compare?
Well, older thermal methods like multi-stage flash, MSF, are much higher, $50, $80, and $833. But modern seawater RO, SWRO, is incredibly optimized, operating down at 3 to Quivor, £15.33.
Wow, so MD, even SPMD using free solar heat, might still need significantly more total equivalent energy input than RO, especially if you factor in pumping energy.
That's often the case, yes. The thermal energy from the sun is free, but converting it and running the system isn't necessarily more energy efficient overall than highly optimized RO for clean seawater.
So why pursue MD-SPMD at all if RO is so energy efficient?
The justification hinges on MD's strengths. Its tolerance for very high salinity feeds where RO fails or becomes exorbitantly expensive due to osmotic pressure, its resistance to certain types of fouling, and its ability to utilize low-grade waste heat or solar thermal energy directly. It targets different, more challenging water sources.
Okay, that context is crucial. Now, what about the bottom line, water production cost?
This is where it gets tricky, and the data varies widely depending on the scale, location, and specific technology assumptions. Traditional large-scale desalination costs are roughly 1.57 for RO, and maybe 1.4 for MSF.
And MD-SPMD?
The reported costs for CMD have a huge range, anywhere from 505 summers in Siri in ideal scenarios with waste heat, up to over 15 level dollars or 33 lars for smaller or less optimized systems. SPMD costs reported in pilot studies currently also span a wide range, maybe the 30 Semirels, 33 lars at the very low end, likely optimistic projections, up to $14 and $15.03.
That's a massive range. What drives the cost in SPMD pilot studies? What are the expensive bits?
The main culprits for the high capital expenditure CapEx are consistently the solar collectors, if using an indirect thermal approach, and the membrane modules themselves, especially if using advanced photothermal materials or fabrication methods.
So the specialized hardware.
Exactly. One study specifically noted that solar thermal collectors accounted for about 25% of the total system cost. Another major challenge is energy storage.
For running at night or on cloudy days.
Yes. Both thermal energy storage to keep providing heat and electrical energy storage, batteries for pumps, are currently quite expensive and add significant cost and complexity, making continuous 247 operation economically challenging for purely solar-driven systems right now.
So high initial costs for the core components and the challenge of intermittent solar energy are the main economic hurdles. This leads us to the critical gaps and future recommendations. What does the research community need to focus on to make SPMD truly competitive?
Top of the list is material science. We absolutely need more durable, long-lasting photothermal materials.
What does durable mean here?
It means materials that maintain high photothermal conversion efficiency, broadband solar absorption, and chemical stability for years, maybe about 5 to 10 years under real-world operating conditions. UV, heat, fouling. And crucially, they must have low toxicity and minimal leaching potential.
So long-term performance and safety validation specifically for SPMD conditions.
Precisely. Second is scalability and design. Research needs to focus on designing modules with effective integrated latent heat recovery.
Capturing the heat released during condensation and using it somehow.
Yes, perhaps to preheat the incoming feed. Recovering that latent heat significantly boosts overall thermal efficiency, but designing compact, cost-effective recovery systems is tricky. We also need serious investigation into constructing larger-scale facilities to understand the economies of scale and bring down overall plant costs.
What about understanding the fundamentals better?
That's key, too. We need to resolve some fundamental mechanisms. For example, exactly how do certain additives like MOFs increase membrane flux even without, obviously, larger pores? What are the precise molecular interactions that allow some dense surface coatings to prevent wetting by oils or surfactants? Deeper understanding enables better design.
And on the operational side, fouling is always an issue.
Definitely. A major breakthrough would be the development of practical self-cleaning membranes. Imagine membranes that could shed foulants or regenerate their surface properties simply through solar irradiation or some other passive mechanism. That would dramatically cut operational costs and downtime.
Where do you see the first big commercial wins for SPMD?
The most promising near-term application focus seems to be treating highly challenging industrial wastewater, particularly produced water from oil and gas extraction, especially shale gas.
Why that specifically?
Because that water is often hot, extremely saline, and full of organic compounds, conditions where RO struggles badly, but MDS-PMD is well suited. The high value of water treatment in that industry could justify the current costs of SPMD.
Finally, what's the most critical step to bridge the gap from lab to market?
We need much more pilot-scale plant operational experience. We have lots of promising lab results and simulations, but we need extensive data from real-world, long-term operation of pilot plants under diverse conditions to truly validate the technology, refine designs, and build confidence for commercial investment.
Moving beyond the controlled lab environment is essential.
Absolutely essential.
Okay, let's try to wrap this up. We've traced the journey from conventional MD, plagued by the inefficiency of bulk heating and the resulting temperature polarization,
Which cools the feed right where you need it hot.
to the elegance of SPMD, using localized surface heating via photothermal materials. This flips the script on TP, enables much higher thermal efficiencies.
And allows effective operation at lower bulk temperatures and, crucially, lower feed velocities.
Reducing scaling risk and pumping energy costs. That low-velocity operation is a unique defining advantage.
It truly is, from a systems engineering perspective. The technology itself, the core principles, seem ready.
But the market hurdles remain.
Yes. While SPMD offers clear environmental benefits and potential for lower long-term operating costs, the industry has to tackle the upfront CapEx, the cost of those advanced membranes, and potentially solar collectors. Improving the long-term durability of these photothermal materials under years of direct sun exposure is the final critical hurdle for widespread adoption.
Which brings us to our final provocative question for you, our listener. We've seen that Nanophotonics-enabled solar MD, NES-MD, seems to overcome the scaling limitations of traditional MD, maintaining performance even in modules 2 meters long. So, Thinking about that scaling advantage, what specific breakthrough, perhaps in ultra-low-cost, scalable application methods for photothermal layers, or maybe a novel, completely passive integrated design for latent heat recovery, what breakthrough would be needed to fundamentally shift the economics, the levelized cost of water, enough to make community-scale NESMD the go-to choice, even potentially displacing RO in certain scenarios?
It's about hitting that sweet spot, achieving near RO cost efficiency while retaining MD's robustness for challenging water sources. That's the integration challenge for material scientists and systems engineers.
A fascinating challenge indeed. We hope this deep dive gave you the detailed technical briefing you were looking for on where sustainable water solutions are heading. Thanks for joining us.